Welcome back. This is lesson 4, year 11, physics. Please make sure you've completed the retrieval quiz to activate your prior knowledge on the previous 3 lessons where we looked at speed, acceleration and distance time graphs. Here is what we've covered so far in the 3 lessons. In lesson 4, we're going to be looking at speed time graphs. Speed time graphs, similar to distance time graphs, but quite different. And we're going to learn about that in a moment. Okay, so what we're covering here is be able to describe the motion of speed time or velocity time graphs and calculate the acceleration on the velocity time graphs. Higher tier only need to be able to calculate the distance travelled from the velocity time graph. Let's get to it then. Should be on page 18. It looks like that. I've just copied that on the right hand side, so I haven't got to write at 90 degrees to my laptop. Okay, speed time graphs, here we go. Just remember, think of speed time graphs and velocity time graphs as the same thing. The words are interchanged, but you've already learned the difference between speed and velocity. I'm not going to read through that. I'll let you read through that. So just pause the video and read through it. But what I want to do now is just draw your attention to this box here. It's asking you to think about what constant speed looks like on a distance time graph. It's a sloping line. Obviously, you fill in your booklet to show that. We looked at that last week. It's constant speed because the distance is changing at a constant rate with time. Now, for a velocity time graph, constant speed would be quite different because the velocity isn't changing with time, meaning constant, then it's a horizontal line. So that's just there to start you thinking about the differences between the two. Now, to the right hand side of those 2 boxes are 4 different graphs. And what I want you to do is to complete the bottom 2. I'm going to do the top 2. The first one, straightforward, constant velocity. I've just covered that. So if it's a constant velocity, then it's going to be a horizontal line because the velocity is not changing. So any horizontal line, just change the pen, going across like that. Obviously, the higher the line's up, the higher that constant velocity. Now, if something is accelerating, the speed is changing with time, and the steeper the line, the faster the speed is changing, or in other words, the higher the acceleration. The word we use, of course, we've used it over the last few lessons, is gradient. The steeper the slope, the larger the gradient. You've learned that in maths. Decelerating, that means that the speed is getting less with time. It's decreasing with time. And similarly, the steeper the gradient, the larger the deceleration. I'll leave you do that one. And also that one there, if something's stationary, I'll give you a clue. It's moving at 0 meters per second. Where would you draw that? Where would you draw that on the graph? These 2 graphs are for you to complete. Let's move on to the next page. On to page 19. Firstly, look at this graph. This is a velocity time graph of Usain Bolt running 100 meters. Difference again here than what we saw in lesson 3 is that this is a velocity time graph. So we're showing how the velocity is changing with time, not distance. Couple of things to watch out for here. Velocity time graphs are even more useful than distance time graphs. Not only can you analyze the motion in terms of velocity, but you can also measure accelerations and calculate distances traveled. Firstly, acceleration. You need to know how to calculate acceleration for both foundation and for higher. To calculate distances from a velocity time graph, that's for higher tier only. Okay. Let's quickly look at this graph. And very simply, if you wanted to work out the acceleration, you look at the change in velocity, we show like that, divided by the time taken. If we wanted to work out his acceleration for the first 2 seconds, the change in velocity is this here, which is about 6 meters per second, and the time taken here is 2. 6 divided by 2, 3 meters per second squared. To work out the for higher tier pupils, to work out the distance travelled in the first 2 seconds, you calculate that area under the graph. And using an equation that you would have used in maths, half base times height of a triangle is its area. The base in this case is 2. Okay, that's shown and highlighted. That's shown there on the graph, the base of the triangle, times the height of the triangle. Here's the height of the triangle, that's 6. So we've got half base times height. Half times 2 is 1. 1 times 6 equals 6. So the area travelled is 6 meters. Looking at the rest of the graph, you can use the same methods for calculating acceleration and distance travelled at different parts of the graph. So if you're asked what was the distance travelled between 7 and 8 seconds, you would calculate the area of that rectangle. So we've already done this further up. It's asking to work out the acceleration for the first 2 seconds. And it's 6 divided by 2, 3 meters per second squared. You see the same graph here again, and there's a couple of questions that you need to do. First one, calculate the acceleration between 2 and 3 seconds. Now, what you need to do here, between 2 and 3 seconds, I'll use a different colour, get a ruler, is just show the two points at 2 seconds, at 3 seconds, and work out the change in velocity, which is in that direction, and the change in time, horizontal. So change in velocity is vertical, change in time is horizontal. So between 2 and 3 seconds is that way. The change in time is just 1 second, and then the change in velocity shown here. We're going to take those 2 points off the graph. It goes from 6 up to 10, 6 to 10. That's going to be 4 meters per second. The time again, is 1 second. So to work out the acceleration for part A, please remember to show the equation, put in the numbers, answer units. Remember back to lesson 1, Eno, the donkey, equation, numbers, answer unit. just makes these calculations so much easier, and also ensures you get the full marks. So I did it for 2 to 3 seconds. What I'd like you to do then, pause the video and you work out part B, 3 to 7 seconds. Then says Usain travelled approximately a constant velocity of 12 meters per second for 1.5 seconds before decelerating. Before the finish, calculate his deceleration over the last 1.5 seconds. So that's assuming his velocity changes from 12 to 11. Oh, so they've done a lot of the work there for you, look, because the change in velocity here is going from 12 to 11. It actually would be a change in -1. It's a deceleration. So remember that. It's a -1, and you put that in the equation, and it's telling you here the time. Moving on to page 21. This really is a recap of what you just learnt. I'm not going to read through all of that, or I'll just be repeating myself. And just remember, as it shows here, only higher tier need to learn that. Question 4, again, is a question for higher tier pupils. So I'm going to asterisk that. Same for question 5. Yeah, complete question 4 and question 5. Moving then on to page 22. There's 5 questions for you to do over the next 2 pages, 22 and 23. Great questions. They get you thinking about how a velocity time graph translates into words. I'll go through the first graph with you, graph A, and then I'll let you do the others. So it's asking, describe the motion illustrated by the velocity time graphs in figure 10.8 for each graph. Calculate any accelerations, decelerations, and distance travelled. So what we've got here really is your success criteria. Calculate accelerations and decelerations. For higher tier only, then you would also calculate the total distance travelled. I'll do, and I'll show how to translate from the graph into words. I made a start underneath, and what I'll do at the end then is colour code to show how each sentence relates to the different parts of the graph. So I just highlighted in yellow there. The object remains stationary for the first 2 seconds. I'm then going to talk about the second part of the graph. I'll just put that in a different colour. You don't need to do that. This is just me explaining, trying to help me explain to help you learn. You can see if it's going from 0 meters per second to 6 meters per second, it's accelerating. So I can say the object accelerates. I'm going to pause there because I want to include the rate of that acceleration. Now, in order to work that out, what I need to do is, I'm going to do my calculations here, is to work out the change in velocity, and that's 6 divided by the time. It's going from 2 to 4, should be using a ruler there. So that's 6 divided by 2, and that's 3 meters per second. The object accelerates at 3 meters per second squared for 2 seconds. From 0 meters per second to 6 meters per second. The final part of the graph is a horizontal line, and if you remember, a horizontal line means a constant velocity. Again, I'll use a different colour here just to explain. At a constant velocity. Now, we want to include as much detail as possible. So by looking at the graph, we can see that that constant velocity, if we come across here, is 6 meters per second. For how many seconds? Let's go back to the graph. It's going from 4 to 10, and that's 6 seconds. For 6 seconds. We haven't quite finished for higher tier pupils, because higher tier pupils also have to include the distance travelled, and we'll come on to that in a moment. But what I wanted to do before we finish that part is just highlight in green which sentence relates to which part of the graph. In order to calculate the distance travelled, we need to look at the area under the graph. So let's zoom in. If you look at the area under the graph, what I'm going to do now is I'm just going to delete or rub out, erase parts of the graph that I don't want anymore. Slight lag. And split up the graph into 2 parts. I can split it up into a triangle and a rectangle. Sometimes you might want to look at certain shapes under the graph as trapeziums and use the formula for trapeziums, which you would have learnt in maths, which is half a plus b over h. But for now, we'll split it into a rectangle and a triangle. So to work out the area of the rectangle, the area of a rectangle is base times height. If we look at the base, let's just highlight, that's going from 4 to 10. And so that's going to be 6 for the base. The height is going from, we can do that on the axis here, it's going from 0 up to 6. You can show it there as well. And that then is the height of 6. So 6 times 6, 36. 36 meters travelled. So that's 36 meters travelled between 4 and 10 seconds. To work out the area travelled between 2 and 4 seconds, what we need to do is use the equation half base times height. And let me just get rid of that green highlighting, and we can zoom in on this triangle. The base is going from 2 to 4, and the height is going from 0 to 6. So the base I could label here base equals 2 and the height equals going from 0 again up to 6. So I've got my base, I've got my height, same old thing, substitute in the equation. Base is 2, height is 6, half times 2 is 1, 1 times 6 is 6. So distance travelled 6 meters. So add that to the bottom of part A. I've just written it in here. This is for higher tier only, remember. So I'll highlight in pink colour what's higher tier. So it's all to do with distance. The object travels 0 meters in the first 2 seconds, 6 meters between 2 and 4 seconds, then 36 meters between 4 and 5 seconds. Total distance travels 42 meters. Your job then is to do the same for B, C, D and E. B is at the top. C, D and E are on the next page, page 23. There they are. Okay, the remaining pages, 24, are past paper exam questions. The F and H that you see here means that it's applicable for foundation and higher tier. You can see why, because it's a question on acceleration. And part B is for higher tier only. It does ask by drawing a suitable tangent and using acceleration equals gradient of a velocity time graph. Now, I'll give you a bit of help on this one. It's asking to calculate the acceleration at 5 seconds. So if you look at 5 seconds here on the graph and you get the ruler, I'll just put a point on the graph where we've got 5 seconds. I think I'll have to zoom in a little just to work out the correct scale for 5 seconds. 2, 3, 4, 5. There's your 5. And in terms of where that is on the graph, let's get our ruler perfectly vertical. Move that over. Okay, now that red mark I've just put on the curve of the graph itself is at 5 seconds. 5 seconds along the velocity time graph. A tangent, you'd have learned this if you've learned circle geometry in maths. A tangent is at that point there where you draw a straight line showing the gradient at that point. By drawing a gradient, or a tangent I should say, to the graph like I've shown, to work out the acceleration at that point, what you've got to do is now take 2 points. I've gone ahead and made some notes on the graph here just to help you work out the acceleration. Effectively, look, you work out the change in velocity, you work out the change in time, put one over the other. We worked out 10 by going from 15 to 25 on the graph and going from 2.5 seconds to 7 seconds at the bottom. The change in time is 7 take away 2.5, which is 4.5 seconds. All that's left to do for you is then complete higher tier, complete part B, and on the top of page 25. Quick task there. I've made a start. All I want you to do is to annotate this graph. So take the different parts of the graph and explain what's happening. Make sure you complete the assessment for this lesson, lesson 4, and see you next time. Bye.